So as we've said, we are designing an asynchronous counter. So our focus is on the asynchronous. We are designing an asynchronous counter. And in this case, we consider where the mod is less than 2 power n. So we said that in any given asynchronous counter, the number of flip-flops will determine the highest count that you can have. For example, like in our previous case, we had 3 flip-flops. That means we could count all the way from 0 to 7. And a count of 0 to 7, these are 8 different counts. And that is why we are calling it 2 power 3, which is equals to 8. And this is our mod. So it's a mod 8 or a mod 2 power 3. At times, we don't want to count all the digits or all the different numbers in between 0 and 2 power n. And for example, if we would want to design a counter that counts from 0 to 4, for example, if you want to design 0 to 4, a 4 is 1, 0, 0. So notice in this case, we would still require 3 flip-flops because 4 has 3 bits, just like 7, which is 1, 1, 1. And in this case, then we will not be using or utilizing all the counts. For us to design a counter whose mod is less than 2 power n, we consider the next count. We consider the next count after the highest count. The next count after the highest count. So our next count, because we are counting from 0 to 4, will be 5. And 5 in binary form is 1, 0, 1. So we will be making use of the next count to reset the flip-flops. So we make use of the next count to reset our flip-flops. In our case, we have used the JK flip-flops, and we noted that in our JK flip-flops, those are the inputs, those are the outputs, and the inverted outputs. The flip-flop has a reset pin and a set pin, and both the set and reset are active low. So this is what we call the active low reset and set pins of the JK flip-flop. So what we do is that we generate an output out of 101, whose overall effect is to give us a 0 that is able to reset the flip-flop, because the flip-flop is reset by an active low input. So in that case, we can use a NAND gate. We can use a NAND gate. A NAND gate pass the outputs of the flip-flop to the NAND gate like this. So if this is our NAND gate, we pass the 3 inputs, but the middle one we first invert it. That's the last one. Then this is the output of our flip-flop. So this is 1, 0, 1. The inputs to the AND gate will be 1, 1, 1, because the NOT gate inverts the 0 to a 1. And you can see 1 and 1 and 1 is 1 inverted, will get a 0. And we can use this 0 to reset our flip-flops. So that at the end of the day, we can have our flip-flops configured just like in a mod 2 power n asynchronous counter, but we make use of the NAND gate to reset our flip-flops. So the entire connection of the counter will look like this. So we have the 3 flip-flops. So if these are the 3 flip-flops, These are the three flip-flops. They will be of JK form, so the JK flip-flops. So we clock only the first one. So this one will be clocked using a clock input signal. And then the output of the first one becomes the clock signal to the next one. So the output of this will clock the next one. And then the output of the second one clocks the third. So you'd expect then the connection to be like this. Then all our JK inputs will be 1. All our JK inputs will be 1, just like in a mod 2 power n synchronous counter we designed before. Then all of them would have a reset pin. So this is the reset pin. This is the reset pin for our flip-flops. And we make use of a NAND gate to reset the flip-flop as follows. So we will have our NAND gate. We have a NOT gate. And the output of the second flip-flop is going to be inverted. So that's the connection you need to make. And that is the second input. Then the third will be connected directly, like so. And then the first one will be connected directly again. So this is the first one, which we need to connect directly. And then this will be connected to our reset pins. So these are the reset pins which we connect to the outputs of the NAND gate, and then our outputs can be tapped at these points. So this will be our outputs, which we can be able to connect to a display section. And through this, then we're able to implement a mod 5. This will be a mod 5 asynchronous counter, counting 0 to 4. 4 digits, 5 digits, 0 to 4, and becomes a mod 5 asynchronous counter. We can simulate these in Proteus. We can simulate these in Proteus. So we will require the 3 flip-flops. So I need the 74, 76, which is the JK flip-flop. These are the 3 flip-flops. We do the basic connections like in the previous case. So we need a digital clock input. So the clock input will only be clocking the first flip-flop. The output of the previous becomes the clock input to the next. So in this case, we expect that connection, and then the output of this one becomes the clock signal to our next flip-flop. So those are the clock signals. Then we need to connect the JK inputs to a high. We can use a DC source, and in all of them, we make sure that the inputs to the JK flip-flops are high. So These are the inputs to the JK flip-flop. These are the inputs. Then we make sure that this is high. So we connect this to 5 volts. Next, we consider a NAND gate, a 3-input NAND gate. So 3-input NAND gate. So a 3-input NAND gate, like this, is what you will need to reset the flip-flops. So you can connect it here. Then to it, I need a NOT gate so that I can invert the second output. We need a NOT gate. NOT gate, which we can rotate, tap the output of the second flip-flop, which is that output, and connect it as the second input to our NAND gate. Then the first or the last input will come from the last flip-flop, and then this first output or the first input of the NAND gate will come from the output of the first flip-flop, like that. Then the output of this NAND gate will go to the reset pins of all our flip-flops. So we connect the reset pins of all our flip-flops like that. Next, we include the display section. So again, the decoder 2446. So this is our decoder. We ground the most significant bit because 4 bits, we are using only 3 bits. So we ground D, then C goes to the most significant bit, B to the second most significant bit, and A to the least significant bit. Next, we include the display section. So we can use a common anode display. This is our display. We can use color red. So we do the connections, they are direct connections. These are direct connections from the decoder to the display. Those are the connections. Then we need to connect this pin to a high, being a common anode 7-segment display. So we connect this to a high and make sure that this is 5 volts. That we are done. Those are the connections we need. We can now proceed to test the circuit. So count 0, 1, 2, 3, 4, back to 0, 1, 2, 3, 4, and back to 0. And that is a mod 5 asynchronous counter using the JK flip-flop. Thank you once more.